Okay, so welcome back to this next video in which we are discussing group automorphisms. Okay, so in the previous video what we saw is that a group automorphism is a set permutation of the set that underlies the group itself, okay, which obeys the property of being an isomorphism. Okay, so it obeys this property that for all G1 and G2 are elements of the group, it is the case that if you take f of G1 composed with G2, that it's equal to f of G1 composed with f of G2, i.e. it does not matter whether you first compose the two elements together in the group, okay, and then take what that answer is mapped onto in the codomain, or if you firstly map them into the codomain and then compose them in the codomain, the answer is exactly the same. Okay, right, so what we now want to discuss in this video is the set of all automorphisms of a group. Okay, so the starting point then is to give you the name for this set of all automorphisms of a group. Okay, so the name is like so. It's written aut for automorphisms, okay, and then you put brackets G, okay. So this is the set that contains all automorphisms of the group capital G. Now quite clearly it is a subgroup of the symmetric group on the set that underlies the group capital G. So SG, remember, the symmetric group on the set that underlies the group capital G. This means the set of all set permutations of the group capital G, okay, and then it will have the composition law of those set permutations of the set that underlies the group capital G as its composition law to form the group of the symmetric group on the set capital G. Okay, so all of these set permutations that are actually automorphisms that obey this isomorphism property, okay, they will be somewhere within the symmetric group on the set G. Okay, so that means that the automorphisms of G is a subset of the symmetric group on the set G. Okay, right. What I now want to show you is that this is actually more than just a subset of this group. Okay, it's actually a subgroup. Okay, so what I want to show you is that the automorphisms of the group capital G is actually a subgroup of the symmetric group on the set G. Okay, so that's what we're going to devote our efforts to in this video. Okay, so whenever you want to show that a subset of a group is a subgroup, what you need to do is you need to show that the subset with the inherited composition law from the larger group, which in this case is composition of the set permutations of the set capital G, okay, which we know is a group, but I'll just refer to it as a set for now, okay. What we need to show is that with that inherited composition law on the subset, it's actually a group in its own right, so we need to make sure that it obeys the four axioms of group theory. And we know that we don't need to worry about the second axiom of group theory, associativity, because if it's a subset with this inherited composition law from the larger group, then the inherited composition law must obey associativity, because after all it's just a subpart of the composition law on the larger group. So if the inherited composition law didn't obey associativity, then it wouldn't obey associativity when it's part of the larger composition law on the larger group. Okay, so because the larger group is a group, its composition law must obey associativity, and hence all of the inherited composition laws must also obey associativity. So whatever subset you take of a group, in fact whatever subset you take of this symmetric group on the group capital G, okay, it will always obey associativity when you have that inherited composition law on it. Even if it doesn't obey the other axioms of group theory, it will hit axiom number 2. Okay, so we don't need to worry about axiom number 2. Just being a subset with the inherited composition law on it from this larger group is enough to say that we have axiom number 2 obeyed. Okay, but we do need to worry about the other three axioms of group theory. So we'll start with axiom number 1. So axiom number 1 is closure. So what that means is that if I take any two elements from this subset of the symmetric group on the group capital G, okay, and compose them together, if I take any two elements that are in my automorphisms of G, okay, so any two elements that are in this specific subset of the symmetric group on the set of capital G, okay, and I compose the two of them together, I must end up with another element that is back within the automorphisms of capital G. So let me write this out. So if we have, and I'll put a for all, so for all F1 and F2, which are elements of the automorphisms of the group capital G, okay, so take any two elements of the set of automorphisms of the group capital G, okay, I need to prove that if I compose them together, so I'll put to show, okay, that F1 composed with F2, where this composition is composition in the symmetric group on the group capital G, okay, so remember that will mean composition of the maps that these represent, okay, I need to show that that is also an element of the set of automorphisms of the group capital G, okay. Right, so I want to show that if you compose it together, any two automorphisms of the group capital G, you get another automorphism of the group capital G. Okay, right, so how am I going to do this then? Well, quite simply, I'm going to use the definition of what it means to be in the automorphisms of capital G. And in fact, I might just write out what the definition of this subset of the symmetric group on the group capital G is actually equal to. So the automorphisms of the group capital G is all mapping, so all F, which are elements of the symmetric group on the group capital G, such that they obey the isomorphism criterion. Okay, so it needs to be the case that for all little g1 and little g2 is an element of the group capital G, that F of g1 composed with g2 is equal to F of g1 composed with F of g2. Okay, so it's all the mappings from the symmetric group on the group capital G that obey this criterion. Okay, right, so I'll just colour this one in. So we need to show then that F1 composed of F2 actually obeys all of this. Okay, now we instantly know that it will be another element of the symmetric group on the group capital G. Okay, because when you compose together two set permutations, we know that you end up with another set permutation. F1 and F2, if they're elements of the automorphism set on the group capital G, okay, they are set permutations of capital G. So when you compose them together as set permutations, you will end up with another set permutation. So we know that it obeys this portion. It is an element of the symmetric group on the group capital G. Okay, what we need to prove is that it obeys this criterion. So let's just write this out. So we need to show that F1 composed with F2 obeys this. And in fact, I should put the for all G1 and G2 bit first. So I want to show for all G1 and G2 are elements of the group, I want to show that F1 of F2 of G1 composed with G2, okay, and this means the two of those composed together, because this means do F2 first and then do F1, and remember that is how you compose two mappings together in the symmetric group on the group capital G. Okay, so I need to show that for all G1 and G2 are elements of the group, that F1 of F2 of G1 composed with G2 is equal to, and now let's have the other side, F1 of F2 of G1 composed with F1 of F2 of G2. And I've dropped the composition symbol for the group. I'm just writing elements of the group next to each other to denote composition. I might just stick it in here because this does look probably a bit more complicated without it. Okay, so it actually might simplify it if I put the composition law in here. So these red dots, these are compositions in the group capital G. Okay, so this is what I need to show. I need to show that these two sides are equal to one another. And what am I actually given to try and prove this? Well, the only fact that I have is that F1 and F2 are both elements of the automorphism set of the group capital G. Okay, so I know that these two obey this criterion, and that actually is all that I need to know. Okay, because let's take this left-hand side here and try and turn it into the right-hand side. Okay, And the way that we can do this is just by using the fact that F1 and F2 are indeed automorphisms of the group capital G. So if F2 is an automorphism of the group capital G, then I can split F2 of G1 composed with G2 into F2 of G1 composed, and I'll need my red pen back again, so red blob for composition of elements in the group, with F2 of G2. And I know this looks complicated, but remember, F2 of G1 is just some element of the group, F2 of G2 is just some element of the group, so I'm just composing two elements of the group together to get another element of the group. And now what I'm going to have to do is take F1 of that answer. Okay, so I've just used the fact that F2 is an automorphism of the group capital G to do that step here, where I've split F2 of G1 composed G2 into F2 of G1 composed with F2 of G2. Okay, now what I can do is use the fact that F1 is a group automorphism to split this into F1 of F2 of G1, and remember F2 of G1 is just some element of the group. Okay, and then I'll need my red pen again, composed with F1 of F2 of G2. Okay, so I've just now used the fact that F1 is a group automorphism to say, okay, I've got F1 of some element of the group composed with some other element of the group. I know that because F1 is a group automorphism, that I can split that into F1 of this element of the group composed with F1 of this other element of the group. Okay, so I'll highlight this up again. So these are the elements of the group here, and I've just split it up here. Okay, and of course what I've now got on this over here is the same as what I've got on the right hand side here. So I've taken the left hand side and turned it into the right hand side, and therefore it's true that this is equal to this for absolutely all little g1 and little g2 that you have within your group, okay, because the arguments that I applied here are valid whatever little g1 and whatever little g2 you were actually using. Okay, so what I have just overall shown is that if I compose any two group automorphisms together, I get another group automorphism. So the composition of two set permutations that are group automorphisms together is another group automorphism. It's another one of these very special set permutations. Okay, so that now proves that this set of all automorphisms of the group capital G is actually closed under composition, where composition means the composition of the set permutations. Okay, so that's axiom number 1 then satisfied. Okay, we're skipping axiom number 2 because we know that that one's automatically satisfied. So let's now go on to axiom number 3. Okay, so axiom number 3 is that we need the identity element from the symmetric group on the group capital G to actually be within our set of automorphisms of the group capital G. Okay, right, so what shall I call the identity element? I cannot call it just E, because E, remember, means the identity element in the group capital G. So I'll call it FE. So let's say FE is the identity element in the symmetric group on the group capital G. So that means that it's the identity map that sends all of the elements of the group onto themselves. Okay, what I need to prove is that this identity element is also within the set of automorphisms of the group capital G, but I've already shown you that. I've already shown you that one of the automorphisms that you can always find, no matter what group you're working with, is the identity set permutation that sends all of the elements of the group onto themselves. I've shown you that that's a very trivial group automorphism, not a particularly interesting one, but it is a group automorphism. Okay, so I've already shown you then that this identity map, which will send all elements of the group onto themselves, and I'll just spell that out, so it'll send all little g onto little g for all little g is an element of capital G. Okay, this is an element of the set of automorphisms of the group capital G. So FE is an element of the set of all automorphisms of capital G. So this is looking hopeful, because now what we know then is that this set of automorphisms of the group capital G does in fact have the identity element from this larger set, the symmetric group on the group capital G, in it. Okay, right, so now we've only got one more axiom to actually prove, and that is the fourth and final axiom of group theory. Okay, so axiom number 4. So what we need to show for axiom number 4 is inverses. So we need to show, and I've missed out the for all sign again, I'll just squeeze that in there. So for all f, which is an element of the automorphism set on the group capital G, okay, I need to show that the inverse map is also an element of the set of all automorphisms of capital G. So I need to show that if I have any set permutation of the group capital G that is an automorphism, that its inverse set permutation is also a automorphism, okay, and therefore that this set of all automorphisms of the group capital G actually has inverses in. Okay, so what I've got to show then is that F inverse, which I know is an element of my symmetric group on the group capital G, is actually an element of the automorphisms of G. Okay, so that's what I now need to show. Okay, so how am I going to show that? Well, again, what I instantly know is that F inverse is another set permutation of the group capital G, so that bit's fine. What I then just need to show is that it actually obeys the isomorphism criterion. Okay, so that it obeys that criterion that it doesn't matter which order you do composition and mapping. Okay, so I need to prove that whatever little g1 and g2 that you pick from the group, okay, so for all g1 and g2 that you can possibly come up with from the group capital G, that it's the case that F inverse of g1 composed with g2 is equal to F inverse of g1 composed with F inverse of g2. And remember again, this is composition in the group here and here. Okay, so how am I going to do this? Well, again, I need to at some point use the fact that F is an automorphism of the group capital G itself, and in fact that is going to be utterly crucial to this. Okay, so let me draw a picture to help you understand this, because this one is the most complicated argument in my opinion. Okay, it's not too bad, but it's the most complicated of what we've seen so far. Okay, so let me draw a picture of F. So it is a map from the group capital G to itself. So I'll colour this in. So here we have the group capital G. This is representing the set that underlies the group capital G. Okay, and we now have F, which we know is an automorphism of capital G. So it is a set permutation, first and foremost, of the elements in capital G onto the elements in capital G. So it's a mapping from G to G, okay, and this is a special mapping because it is bijective, okay, and initially that's the only bit that I want. We'll need the fact that it's an actual automorphism in a moment, but at the moment let's just think about the fact that it's bijective. Now, the fact that it is bijective is very interesting to me because it means that whatever little g1 and g2 you pick, I can find you some g1 bar and g2 bar in the domain over here. Okay, so I'll put a g1 bar here and a g2 bar. So I can find elements in the domain here that are being mapped onto each of these elements. Okay, so my claim is that I can find a g1 bar such that under the mapping F it is mapped onto g1, and I can find a g2 bar such that under the mapping F it's mapped onto G2. So you give me any G1 and G2 you like. I can find these elements, which I'm calling G1 bar and G2 bar, such that when I map, use F, apply F, this mapping to them, I get G1 and G2. Okay, and that's quite simply because this is a bijective map, so it's surjective in particular, which means that every element in the group here in the codomain group here has another element in the domain group over here that's being mapped onto it. Okay, so quite simply you can find G1 bar and G2 bar such that this is true. Okay, and we're going to use this fact. Now we're going to use the fact that F is an automorphism. Okay, and the way we're going to use the fact that F is an automorphism is I can compose G1 bar and G2 bar together in my domain here. Okay, so these elements that I've just found, G1 bar and G2 bar, I can compose them together in my domain here, okay, and get G1 bar composed with G2 bar. Now, if I ask what is f of G1 bar composed with 2 bar, okay, so if I ask what is f of G1 bar composed with G2 bar, what is the answer? Well, because this is a group automorphism, I can split this into f of G1 bar, okay, composed with f of G2 bar, okay, and of course the answer to f of G1 bar is just G1, and the answer to f of G2 bar is just G2. Okay, so the answer is G1 composed with G2. So that's really a nice picture of what it actually means to be a group automorphism there. Okay, that really you can compose these two elements together in the domain, and what that will be mapped onto is the same as what these two elements are in the codomain composed together. Okay, so that's all rather lovely. Okay, and now we have enough to prove this statement. Okay, right, so I'm going to use this final line here to prove this statement. I've got this statement that for G1 composed with G2, this is equal to this f of G1 bar composed with G2 bar. Okay, where you can find G1 bar and G2 bar, as I said from my first argument here. Okay, and I am now going to stick this equation here into here basically. Okay, for G1 composed with G2, and then what I will get is the f inverse of f of G1 bar composed with G2 bar. Okay, so I've just stuck in for G1 composed with G2, f of G1 bar composed with G2 bar. You can do this. There's nothing stopping you from being able to do this. You can find G1 bar, you can find G2 bar, and you can express G1 composed with G2 as f of G1 bar composed with G2 bar. You can do that no matter what little G1 and what little G2 you picked from the group. Okay, so you can't stop me doing this basically. Right, and now I use the fact that f inverse is the inverse map of f to say that the answer here is G1 bar composed with G2 bar. Okay, so that's the answer then to the left-hand side here. What I want to show is that I can reduce the right-hand side here of this equation into the same thing, and therefore that these two must be equal to one another. Okay, so now let's do the right-hand side, and this is simpler because all I can now do is say, okay, let's replace G1 and G2 in here with f of G1 bar and f of G2 bar respectively. So I'll just replace G1 here with f of G1 bar. Okay, again, you can't stop me doing this. And then I'll replace G2 here with f of G2 bar. Okay, like so. And then on this side I've got f inverse of f of G1 bar composed with f inverse of f of G2 bar, and again the f inverse and the f cancel, okay, and this side then is just going to end up as being G1 bar composed with G2 bar. So through this method I have reduced this one and this one into being the same thing, okay, and there's nothing wrong with my method. For whatever little G1 and G2 you have, it is totally valid that you can rewrite this one as G1 bar composed with G2 bar, and that you can write this one as G1 bar composed with G2 bar, where the way that you find G1 bar and G2 bar is like so. You quite simply say what element in the domain is mapped onto G1 to find G1 bar, and what element in the domain is mapped onto G2 by f to find G2 bar. Okay, so that's the way that you can then find G1 bar and G2 bar. So what I've now proven then is that if f is an automorphism of the group capital G, then its inverse set permutation, f inverse, will also be an automorphism of the group capital G. And with that, we have finally then proven that this set of all automorphisms of the group capital G, which is a subset of the symmetric group on the group capital G, is in fact a subgroup. So it's a very special subset of the symmetric group on the group capital G. It is in fact a subgroup. Okay, right, so we'll have a break there, and in the next video what we will discuss is the concept of an inner automorphism.